Alright, so remember yesterday we started talking about approximation for area under the curve. We said that our goal, what we're going to get to, is what we call integrals or antiderivatives, which is our algebra way of finding this area under the curve. Right now, we're not there yet. We're just looking at graphs. And so basically what we did here, we didn't label it as such, but this is what is called a Riemann sum. So a Riemann sum is going to be an approximation of the area under a curve. Okay, now we do have a couple different types. So we looked at our left and right Riemann sum yesterday. There we go, 2 ends. Okay, and so our left and right, so our left Riemann sum is where our height is equal to the left endpoint y value for like each interval that we're looking at. Okay, for your right Riemann sum, it's the other one. It's the height is equal to the right endpoint y value. Again, for each like sub interval. So we are like summing together a bunch of rectangles. Okay. We kind of looked at it a little bit yesterday. So the graph that we looked at was increasing, yes, because it was a quadratic. And when we have an increasing function, our left Riemann sum is going to be an under approximation. And our right Riemann sum will be an over approximation. If it's decreasing, then they flip. Okay. Now the last one we vaguely talked about it. There are 2 different ways you can do your midpoint. The first way, which is usually how we're going to look at it, is that your height is going to be equal to the y value of the midpoint for each interval. The other way is you can do your left and your right Riemann sums and then take the average of those 2. But usually if they just ask you to do the midpoint, it's just easier to find the midpoint of each interval and find those y values than it is to do a left, then a right, and then average those together. Okay. Now, we looked at yesterday, we were...
Attention staff and students, please listen closely. The emergency has ended. Please return to scheduled activities at this time. Attention staff and students, please listen closely. The emergency has ended. Please return to scheduled activities at this time.
So, yesterday when we were doing ours, we just kind of picked, we're going to do 10 rectangles. Yes? It didn't give us a certain number, it just kind of made sense. But sometimes, if we want a specific number of intervals, so let's say n intervals, we can find the width, okay, of each of our like rectangles, okay, is going to be equal to b minus a divided by n, or the interval a to b. Right, so like on the one we did yesterday, we were going from 0 to 10. So if instead I had said that we wanted 20 intervals, right, we would have to do 10 minus 0 divided by 20. So our width would have been 1/2 instead. Does that make sense? Because sometimes the question will give you a specific number of intervals that it's wanting you to use. Yes, Roland? So we looked at one from a function, right? We had t squared yesterday, which we were able to graph. Sometimes, our favorite kind, we will also be given tables, and we still want to find an approximation for that area. But we don't have a function to plug into if we're just given a table, so we just have to use the table values. So that's what we're going to look at next. Everyone have all that down? Questions so far about any of the definitions? I know it's a lot of information up front, but we kind of have to get it all down before we can kind of look through some examples. Alright, so it says over a 12-second interval, a car's speed is never decreasing. What does that mean? It's
going faster.
It's going faster, right? So it's increasing, it's going up. We don't necessarily know what it looks like, right? But we do know that it never goes back down. So it could be a linear graph. It could be something more like a quadratic or an exponential. We don't quite know, but we do know that it's never decreasing. Yes? And then we're given a table. So we want to find, okay, a left and a right Riemann sum here. But again, this time we don't really have more than just the table that they give us. Now it is important to notice our x values, or like our inputs are time. What are our outputs? Speed, right? And this is important, okay? Because if I'm wanting to find, again, accumulation or total distance, remember that we said it's the accumulation of the rate of change. It's not the accumulation of the distance, right? We can't find the area under the curve for the distances. We want to find the area under the curve for the rate of change, which is speed. Are we all with me there? Okay. So, how many intervals do we want to do? How many intervals can we do, really? Can we do 12 intervals? Do we have enough information? Like, if I wanted to go from 0 to 1, do I have enough information to do a right Riemann sum to go from 0 to 1? No, because I don't have a data point at 1, right? So I am going from 0 to 12. This is kind of where I talked about on our first one, we could do 10 intervals. That makes sense. On this one, how many data points do they give us? 5, right? But notice that if I do a left Riemann sum, I would be going from 0 to 3, 3 to 6, 6 to 9, and then 9 to 12. Yes? And then for my right, I would still have these same intervals. I'm just using my right data point now instead. So really, what's the largest number of intervals that we can do? 4. Are we okay with that? Right? I can go from 0 to 3, 3 to 6, 6 to 9, and then 9 to 12. Yes? What is our width, okay, for each of those? 3. Are we all okay with that? Yes, so maybe. So the width of each of our rectangles is going to be 3. So 3, 6, 9, 12. Now remind me, how do I find my height? Go back to your definition. I'm looking at a left Riemann sum. The left endpoint y value. Okay, so for my first interval, 0 to 3, what's the left endpoint of that interval? 0. And so then what's the y value at 0? 30. So this is at 30. This is not drawn to scale, but I don't have marks up there, so we're just going to go with that. So that means that the height of my first rectangle is going to be 30. Yes? Okay. So then my second interval is from 3 to 6. So on that one, what's my left endpoint? Here. The 3. And what's our y value for that? The 37. Yes? Okay, for our next one, what's our left endpoint? The 6. And what's our value going to be there? 45. The 45. And then lastly, on our last interval, 9 to 54. Yep, so I get something that looks like that. Again, I don't know what this graph looks like, but I know that these would be the values that I would use to approximate it. So then, remember that we want to sum together all of those rectangles, and we are specifically using the left rectangles. So what is our formula for the area of a rectangle? Base times height, which technically here we're calling our base width, right? So it's going to be width times height. Y'all agree with that? What is my width for all of those? 3. So are we all okay that I can just factor out a 3 from everything, and then we don't have to worry about multiplying it by 3 each time? Yes? So if your widths are even, then you can end up just putting that number in the front. Yes? Okay. And then again, we're just using those left y values. So we have 30 plus 37 plus 45 plus 54. So if we add all those together, what do we get? Agreed. And we are in what unit? It'd be feet, right? Because remember, this would be the total distance once I've found the area under the curve. So remember, when we multiply, my y values are going to be, my x values are going to be in hours. My y values, this one in seconds, in seconds. My y values are in feet per second. So my seconds end up reducing out, and we would just be left with feet. Yes? Now, is this an under or an over estimate? Yeah, so again, we don't know quite what it's going to look like, but we do know that it is increasing. Yes? So and if it's a left, then all of those would have to be under whatever my graph is. Yes, no, maybe? Is our setup for the right Riemann sum going to be similar? Yeah, what's the only difference going to be? We're going to use the what values? Right endpoint. Y values. Agreed. So I want you to do that one on. Tell me what you get. we get answers? Yes, no, maybe?
600 feet?
Hmm?
600 feet?
Straight 600? Should be 603. So for our for our right one this time, we're going to use our 37 from 0 to 3. Then we would use our 45 for 3 to 6, our 54 for 6 to 9, and our 65 for 9 to 12. Again, we can factor out that 3, so we would have 3 times 37 plus 45 plus 54 plus 65. So you should get 603 feet. You might just type one of your headings from.
Yeah, type in 64 instead of 65.
Yeah. And then remember that this one would be what? What type of estimate?
Overestimate.
It's going to be an overestimate. Are we all okay with that? Yes, no, maybe. Sounds good. Alright, let's do, okay. So this one, we're still wanting to use a left Riemann sum, okay? We don't necessarily have to graph it this time if we can kind of figure out our information. What do we notice about our numbers this time, though? They are increasing again. Anything else? Our widths aren't the same this time, okay? And that's okay. They don't have to be the same, right? It just means that some of our rectangles are going to be a little bit wider than others. And really, the only thing that changes is instead of, like on our last one, just being able to put that 3 in the front, okay, we're not going to be able to. We're going to have to find the width for each individual rectangle. So again, remember that this is the sum of your width times your height. And so we're specifically using the left endpoint again. So what is the width of that first interval? 2. Okay, and then we're wanting to use what? Which height? The left one. So what's our y value for the left one? 2. And I'm going to add, what's the width for my next one? 3. Again, we're wanting to use the left endpoint. So what's our left endpoint y value? 3. Okay, so this is our 0 to 2, 2 to 5. What's our width for 5 to 7? Okay, and this time our y value is going to be the 5. And then lastly, our width for our last interval is 3, and our height would be a 7. So we get 4 plus 9 plus 10 plus 21. Yes? And what does that give us? 44. Sounds good. We don't have any type of unit this time, so it's just 44. Is that right? One question we have there. We also don't know if it's consistently increasing or decreasing. So we can't say if it's an over or an underestimate. So that's just our answer. which is basically pretty much the same as our Riemann sums. The only difference is now, instead of summing together our width times height, we're going to sum together height times base 1 plus base 2 divided by 2. So this time your height is still going to be the width of each interval. Your base 1 is going to be the y value for the left endpoint of the interval. And your base 2 is going to be the y value for the right endpoint of the interval. So it's kind of combining a left and a right. Let's look at an example. So this says approximate the area under the curve of f of x equals 4 natural log of x on the interval 4 to 10 using 3 trapezoids. So on this one, especially because we have a function, it's sometimes helpful to go ahead and graph it. Do we know what that graph looks like? What do our logarithmic graphs look like? That's one of the ones that we should know.
Concave down, increasing.
Correct. And what else about it is important? What kind? It does not. Your exponentials have a horizontal asymptote at 0, right? Because they stop and get bigger from 0. But remember, since natural logs are the inverse of that, the x's and y's get flipped, so we have a vertical asymptote. Okay, and then the 4 in the front just stretches it, so like it will be going up a little bit faster than our normal natural log. Yes? So, here's a question. Could we have gone, say, from 0 to 10? Why not? Correct, because I have an asymptote at 0. So you would actually be looking at an infinite area. Yes? And we do not deal with infinite areas in Calc AB. If you continue on into Calc BC or Calc 2 in college, you do deal with infinite areas. So, little preview.
That's tough.
It's kind of cool. But you can find the area of an infinite area. So, there you go. But for us in this case, we're going from 4 to 10. Okay. Remember that this point on our axis is going to be at 1, 0, so we know that it's going to be a little bit a ways from that. Yes? So, how do I find my widths in this case? Which, remember, our widths are also going to be technically the heights for our trapezoids. So this time they did give us a specific number. So So what was our label formula?
B minus A over N.
Yeah, so it's B minus A over N. So my B is 10, my A is 4, and my N is how many intervals or how many shapes we're wanting. So in this case, that's 3. So what did we get there? 2. Yes, no, maybe? Which means that our intervals are going to go from what to what? We'll start at 4. So 4 to 6. 6 to 8. And 8 to 10. Right, I'm okay with that. Now this time, how are we going to have to find our height? Or sorry, our base is like a, what's that word? The length of your base 1 and base 2 for each one. So I'm drawing 3 of these. I'm going from 4 to 6, 6 to 8, and then 8 to 10. And remember that we want to draw trapezoids this time. So how do I find where those top points are? Agreed, right? So like for my left dots, I'm going to plug in the left endpoint. From my right dots, I'm going to plug in my right endpoint, okay? So this is going to be, we said that our height or our width, okay, remember that that's the same thing for our trapezoid. So we have B1 plus B2 divided by 2. What's nice about that? Oh, I choose reduce out, so we really only end up with the sum of our B1s plus B2. Yes? So, let's break it down into, on our first one, we're gonna plug in a 4 for our left endpoint, yes? So we would have 4 natural log of 4. Agreed? Then what would I have for my right endpoint on that first one? So my right endpoint is at 6, so we're going to plug 6 into our function. So what do we get? 4 natural log of 6. Agreed? Now, the thing to notice is that my right endpoint for my first interval is also going to be the left endpoint of my next interval. Yes? So, that one is going to start at 4 natural log of 6. And then what's the right endpoint going to be at? 4 natural log of 8. And then the whole plus. Again, my starting spot for my last interval is going to be the ending value for my second to last one, plus 4 natural log of 10. Okay. Now, I tend to write it out like this. There will be, like if you're looking online sometimes, you'll see people go ahead and like double the middle ones, right? So you would see them write it out as like 2 times 4 natural log of 6 plus 2 times 4 natural log of 8, because since those are the intermediate ones, there's going to be 2 of those. I tend to like to write it out more like this, because sometimes I think if you try and combine too many things too quickly, then you forget, well, which one gets the 2 and which one doesn't. But if you see that formula floating out there somewhere, or like a video, and that makes more sense to you, you're welcome to use that method. But like I said, I will just be putting it on the board this way. Okay? Now, if this was a non-calculator active question, that's our answer. Wait with me? It's like natural log of anything other than like E, right, is going to be a not nice decimal, right? Now, if it is a calculator active, then we're going to plug all of that into our handy dandy calculator. And are we all okay if I just tell you that it would be approximately 45.725? Yeah, we all know where our natural log button is on our calculator. That's the biggest part for that one. And then just making sure that you type it in all in correctly. Yes, no, maybe? Okay. We have one last quick example. So it's actually using the same function, okay? But what does it ask me to do this time? Which, if we think about it, ends up being relatively not bad. Because if I'm doing 3 again, we said that our widths are still going to be what? 2. Right? So finding the midpoint for that isn't all that bad. Agreed? Now, there will be some times that if you have a midpoint formula, you might end up having to do like a 0.5 or a fraction. So that's not the end of the world. However, if we like it when they do. So again, we're wanting 3 intervals. They're going to be 1. Okay. So we are going still from 4 to 6 and 6 to 8. Okay. But this time, again, midpoint is still a rectangle. Okay. But instead of using 4 or 6, when it's my midpoint here, what are we using instead? So what's the middle number between 4 and 6? 5. Right, so we're using 5 as my input there. What are we using as our input for 6 to 8? 7. And our input for 8 to 10 is 9. So like I said, that's why we like it when it ends up being nice pretty numbers. But it doesn't always. So, again, switching gears in our brains a little bit. We just got done with a trapezoid formula. However, remember, this one is a rectangle formula. Okay? So we are back to our width times height. Okay? So for all of these, our widths are going to be 2. So I can go ahead and factor that part out. Yes? So this time for my height, for my first interval, we would be using 5. So what is our height there when we plug in 5? Or natural log of 5. Plus, we're using 7 for our second one. So we'd have 4 natural log of 7. And then for our last one, we would have 4 natural log of 9. And we're going to go ahead and leave it like that. We're going to say, this one, especially like on a non-calculator active, if they're asking you to use a midpoint, this is pretty common, where you would have numbers that end up being nice, right? If it was a non-calculator active, that's usually where they would give you ones where you end up with decimal or fractions. The only thing that you might see is because there's a 4 in all of them, you might see like the answer in the book, or like if it was a multiple choice question, they might factor that 4 out as well, right? Like that would be the only thing they might do. So, what questions do we have about any of our left, right, midpoint,